Let's look at the address translation. We have to virtualize the memory address so that individual process has an illusion that it has its own separate and independent and isolated memory address space. So, most important thing is that address virtualization, memory space virtualization, is achieved by the collaboration between hardware and operating system. So OS and hardware should collaborate to provide an illusion that every process has its own address space, and a process has its own virtual address space. And however, all the contents or all variables, pointers, strings, and everything are stored in physical DRAM. So everything is stored in physical entity, physical memory. However, process address space is virtual. So we have to have a mechanism that transforms a virtual space to the physical space. The address translation is performed through the collaboration between the operating system and hardware. And we are going to deal with what each of these are. Let's look at the example. There are small C language code. And there is local integer variable. It contains 3000. And then it increases the value of x by 3. So this is a very simple code. It loads a very value from memory to CPU. This is CPU. And there's memory. And somewhere there is a value 3000. And operating system in hardware, only the CPU can do arithmetic. So operating system has to load the value of 3000 from memory to some register on CPU and increases it by 3. And then saves 3003 back to its original place, overriding 3000 with its new value 3003. So let's going to take a look at about how it is being executed. Let's first compile the program and assume that this is the code that has been compiled by the program. So first, it loads a value pointed by EBX to the register EAX. Let's say this is the location of where 3000 is stored. And then it adds 3 to the EAX register, and then it saves the value of EAX register to the same address which it has been read the 3000 values from. So it loads the value at the address into EAX register, add 3 to EAX register, and store the value to the EAX back into memory. Okay, this is what is going to happen. In the process virtual address space, there is code segment, heap segment, and stack segment. And in the stack, there's local variable that contains 3000 as its value, and the location of that variable is 15 kilobytes. And then stack starts from 16 kilobyte. As you can see that the total size of the virtual address space for a process is from 0 to 16 kilobyte. So total address space is 16 kilobyte for this process. And there is code segment, heap segment, and stack segment. There's only 3 segments here. And at the code segment, there are 3 assembly instructions are loaded, and the corresponding addresses for these instructions is 128, 132, and 135. So let's examine how each of these instructions are executed. First, it fetches the instruction at the address 128, and then execute this instruction. This instruction loads the value from 15 kilobytes. As a result, the EAX register becomes to contain 3000. And then it fetches the instruction, which is stored at address 132. Then execute the instruction. The instruction at 132, address 132, is add. So it does not have any memory access. And then as next step, it fetches the instruction at address 135 and execute the instruction. This time, the instruction is to store the value of EAX register to the address 15 kilobyte. So as a result, 15 kilobyte offset will contain the value 3003. Okay, so however, these are the virtual address space we have executed in the previous slide. And this is physical memory. Let's assume that computer has 64 kilobytes of DRAM. Operating system, when the operating system first creates the threads, it has to allocate the address space for this process. This process contains code segment, heap segment, and stack segment. And at the very beginning of the computer history, the most primitive way to create the virtual address space for a process is to allocate entire virtual address space in the consecutive region in the physical DRAM. So in this example, a process has 16 kilobytes of virtual address space, even though lots of addresses remains unused. Only the small part is used as code. Only a small portion of the virtual address space has been used as a heap. Only the small part of the virtual address space has been allocated for a stack. And dominant fraction of the virtual address space was free. However, in very early days, operating system allocates entire virtual memory space for entire virtual address space for a process. So here, in this 64 kilobyte physical DRAM, operating system finds 16 kilobytes of free memory chunks starting from 32 to 48, and then it allocates the virtual address space for this process. And then this is what we call dynamic relocation. So entire virtual address space is relocated to the physical address space somewhere between the available physical DRAM. For dynamic relocation, the hardware provides two registers, base and bound register. Base register denotes the starting address of the virtual address space in the physical memory, and bound register denotes the valid address region starting from the base. In this example, the base register value is 32 kilobytes, which is the start address of virtual address space is loaded into physical memory, and then bound register denotes the size of the virtual address region, which is 16 kilobytes. So in dynamic relocation, when a program starts running, operating system decides where in physical memory process address space should be loaded, and then it sets the base register value. And then every time it performs address translation, every virtual address space must not be greater than bound, and it should not be negative. So for every memory access, the hardware has to check the given virtual address access is valid or not via checking this condition. The virtual address space is greater than 0, greater than or equal to 0, and less than bounds. Let me give an example. Let's say this is virtual address space, and there were 3 lines of code. Each lines of the code was saved at 128, 132, and 135 address space. So first example, first line of the instruction is move the value of 3000 to the EAX register. So first thing the operating system has to do is that operating system has to fetch the instruction at address 128. So this address translation is performed by the offset is 128, and then it adds the base register value to a given address. It results in 32,896. So this is the physical address of the first instruction it needs to fetch. And then after it fetches the instruction, it executes the instruction. And then in the course of executing this instruction, it has to access the memory. And then it are accessing the virtual address of 15 kilobyte. This is virtual address. So the base and bound register supported hardware automatically translates this 15 kilobytes address to 15 kilobyte plus 32. The result is 47 kilobyte. So it loads the address of physical address of 47 kilobytes. It accesses the rest of the instruction the same way. There are two types of bound register. First one is the size of the address space. Here, the bounds is 16 kilobyte. And then another way of specifying the bound register is specify the actual last address of the address space. In this case, bound will contain 48. To support dynamic relocation, the system requires some hardware support. First one is privileged mode. Hardware should support the privileged mode so that the application programmed prevent the user mode process from executing the privileged operations. And then the system support should have base and bound register. For each process, it needs a pair of register per CPU to support the address translation and bound checks. Then the hardware should be able to translate the virtual address to physical address, and also it should be able to check if the address is within bound limit. And it requires privileged instructions to update base and bound registers. And also it requires privileged instructions to register the exception handler. And also the hardware should have an ability to raise exceptions when a process tries to access privileged instructions or out of memory. Combined with the hardware support, there are a few operating system related issues for virtualizing the memory. OS must take actions to implement base bound approaches, and there are three critical issues. First one is the operating should do some allocation when a process starts, and the operating system should reclaim all the memory a process has been using when a process is terminated. And when a context switch occurs, operating system has to save and restore the base bound register pair. So let me explain each of the three issues one by one. When a process starts, the operating system must find a room for a new address space. Operating system has to maintain a list of free memory chunks. If you look at this physical memory, then from 0 to 16, operating system code is loaded. And then here, from 16 to 32, this memory chunk is free. And also to 48 to 64, the memory chunk is free. So operating system maintains a list of free memory chunks, and here there are two memory chunks in the system, size of 16 kilobyte and this one with size of 40 kilobytes. So when you create a new process, it has to first allocate the memory chunks for a process, and operating system has to look up the free memory list to find the locations. The second issue is to reclaim the memory spaces that has been using by the memory when the process terminates. Operating system must put the memory back to the free list when the process terminates. Let's look at the example. At the beginning, there are two nodes in the free list, size of 16 kilobyte and the other one with size of 48 kilobytes. Now the process A terminates. Because the process A terminates and it has been using 16 kilobytes of free physical memory, after the process terminates, the operating system has to put the address space that has been used by process A to the free memory list. From 16 and 48, these two nodes has been existing before addition, and then a new node with 32 kilobytes is added to the free list. The one thing you have to remember is you do not have to maintain the nodes with some order. In this example, the nodes are sorted with the address of the individual memory chunk. But of course, you can, in your implementation, you should be able to add, you can add this 32 kilobytes memory chunk next to the memory, or also you can add the newly added free memory chunks at the beginning of the linked list. It depends upon the implementation. And of course, another important part you have to remember is now you are using the linked list to find the memory list, but you can use hash data structure or other data structure for efficient manipulation. And third issue is context switch. When you have to switch the processes, the operating system has to save and restore the register pair. And the operating system has to define where you should store the base and bound register, and then where you should restore the base and bound register value from. Here, there are two processes, process A and process B. And at the beginning, process A was running, and base register value and bound register value was 32 and 48 respectively. Then, after context switch, the CPU, the operating system decides to run process B. Now, the process B was now loaded at starting at 48 kilobytes, and whose size is 16. Now, the base and bound register needs to be switched from 30 to 48 pair to 48 to 64 pair. So before, in the course of switch the context, operating system has to store the previous value of base and bound registers to somewhere, and operating system has to define where it has to save the values. In this example, it saves the value at process control block. The process control block PCB corresponds to struct thread in our operating system PINTAS. Also, when the exceptions occur, for example, the application tries to access the address outside its memory address region, or an application tries to access the address that has been occupied by operating system, the privileged area, then operating system has to raise exception and execute the exception handler. So there are two things the operating system has to do. First, it has to define the exception handler, and then second, operating system has to inform where the exception handlers are. This is performed at boot time. In summary, as a very basic forms of separating the virtual address space and physical address space, we have explained the base and bound register approach. And to separate the virtual address space and physical address space, it requires address translation. And to perform address translation, there has to be a support for hardware and also for the operating system. But there is a fragmentation issue. It is called the external fragmentation. Every process may have different virtual address space size. So as the operating system allocates and deallocates repeatedly, In the physical memory, there can be a large number of small free memory region which cannot be allocated to any processes because it is too small. That is called external fragmentation. So branch and bound register approach is subject to fragmentation issue.